Air travel permeates our routines, but it comes with significant environmental costs. Carbon emissions contribute to global warming and climate change, raising concerns. However, imagine the possibility of carbon-free flights. China made this a reality with the creation of the plasma electric engine, a revolution for aviation. With this invention, air travel can abandon carbon emissions, paving the way for a sustainable future. Let's examine this remarkable engine, its operation, and its implications for aviation. In recent times, plasma engines have gained ground in space exploration. These systems use plasma to generate propulsion. Although the technology is still in its early stages, researchers see it as a solution for carbon-free air travel. Unlike traditional systems based on chemical reactions, plasma engines employ electric and magnetic fields to ionize gases like xenon, argon, or krypton, generating plasma. This plasma is then accelerated to produce a force that propels the spacecraft. Plasma engines can achieve escape velocities superior to those reached by chemical rockets, making them ideal for long-duration space travel. These engines differ from ion thrusters, which generate thrust by extracting current from a plasma source. Ion thrusters use grids or anodes to accelerate ions, whereas plasma engines use internally generated currents, such as high-current electric arcs between two electrodes, to accelerate ions. This results in lower escape velocities but with high thrust efficiency. Plasma engines offer significant advantages, including propulsion efficiency. They require less fuel than traditional rockets, making them more economical and eco-friendly. They also have extended lifespans, with some models functioning for consecutive years. Additionally, plasma engines can be throttled, providing precise control over the spacecraft's speed and direction. Furthermore, they do not need high-voltage grids or anodes to accelerate charged particles in the plasma source, reducing the risk of ionic erosion of the grid and simplifying the engine's design. Plasma exhaust is nearly neutral, allowing the use of ion and electron recombination in the exhaust plume to neutralize it, eliminating the need for an electron gun. These engines produce plasma sources in various ways, such as radio frequency or microwave energy through an external antenna. They display propellant versatility, including argon and carbon dioxide. Testing of these engines occurs in space missions like NASA's Dawn, exploring the asteroid belt, and the European Space Agency's Bepi-Colombo, heading to Mercury. Plasma engines are in the early stages of development and require further research for broad applications in air travel. Despite their promise for space travel, they have some disadvantages. One of them is the high energy demand, such as the Versma VR200 engine, which requires 200 kilowatts of electrical energy to produce only 5 newtons of thrust. In other words, for space missions, massive energy is needed. The integration of the engine with other components, such as fission reactors, could increase the spacecraft's weight, challenging space launches. Another disadvantage is plasma erosion, which occurs when the plasma thermally ablates the walls of the thruster cavity and support structure, potentially causing system failure. Therefore, new materials and cooling systems are needed to prevent erosion. The relatively low thrust of plasma engines implies that they are not practical for launching a spacecraft into orbit, being useful only for space operations. In contrast, chemical rockets, providing more thrust, are better suited for launching spacecraft into orbit. Despite these disadvantages, several space agencies have developed plasma propulsion systems, such as NASA's Hall effect thruster and Viasec, and the Westman engine from Herastra's rocket company. These engines are already operating in space and hold promise for reducing travel time between planets. The recent China's plasma electric engine marks significant progress. This new engine, designed to operate on Earth, advances towards carbon-free air travel. The technology could power aircraft and minimize carbon footprint, making air travel more sustainable. In recent years, China has heavily invested in plasma engine technology and improving air travel. In 2018, the Aero Engine Corporation of China, AECC, announced plans to develop the CJ1000AX turbofan engine for commercial aircraft, aiming to reduce fuel consumption, emissions, and improve performance. In 2020, engineers from the Wuhan University Institute of Technology presented a functional prototype of a microwave thruster. According to them, it can operate in Earth's atmosphere with efficiency and thrust comparable to jet engines. This innovative plasma engine uses electrified air instead of gases like xenon, making it more practical for our environment. The thruster creates thrust by generating plasma from a gas source that is heated and rapidly expanded. The new invention uses ionization to produce low-temperature plasma, fed into a tube and bombarded with microwaves. The microwaves shape the ions, which then collide with non-ionized atoms, producing considerable amounts of thrust. The device includes a flattened waveguide and a 2.45 GHz, 1 kW magnetron, specifically designed to concentrate the microwaves. This increases the strength of the electric field and maximizes the amount of heat and pressure in the plasma. Through a hole in the waveguide, a quartz tube is inserted. Air is forced through this tube, passing through a small section of the waveguide, and exits at the core's ends. As the plasma heats up to over 1000 degrees Celsius, it generates a torch-like flame. As the hot gas leaves the waveguide, thrust is created. Tests have shown that the engine can produce up to 500 newtons of thrust and operate continuously for 30 minutes, applicable to modern aircraft. Engineers have realized that adjustments to the airflow in the compressor could generate a more extended flame jet, increasing the microwave power. Common jet engines rely on burning fossil fuels. This process releases pollutants into the atmosphere and contributes to climate change. Plasma engines, on the other hand, use electricity to ionize the air, creating a plasma that emits a stream of charged particles at high speeds. This flow can generate thrust. One of the main attractions of plasma engines is the reduction of carbon emissions. A study conducted by the University of Illinois at Urbana-Champaign indicates that plasma engines could reduce carbon emissions by up to 60% compared to conventional jet engines. The emissions reduction would help the aviation sector achieve its carbon reduction goals and contribute to global efforts to combat climate change. Another advantage of plasma engines lies in fuel efficiency. Current jet engines have an efficiency of only 25%, indicating that 75% of the fuel's energy is lost as heat or noise. However, it is expected that plasma engines will have much higher efficiency, potentially doubling or even tripling the efficiency of conventional engines. This could lead to lower fuel costs for airlines and reduce the dependence on fossil fuels. However, despite presenting such potential benefits, there are considerable challenges in transitioning to plasma engines in air travel. One of the main challenges lies in scalability. Chinese researchers who developed a new plasma engine tested it on a small scale, and it is still uncertain whether the technology can be scaled up to power commercial aircraft. This will require significant investments, research, and overcoming technical challenges related to energy generation and storage. Another challenge is the cost of developing and implementing plasma engines. Although the reduction in carbon emissions and increased efficiency may result in cost savings in the long run, there are relevant initial costs associated with the development and testing of the technology. There is also the challenge of safety. Plasma engines emit a stream of charged particles at high speeds, which can pose a safety risk if not properly controlled. Additionally, there is the risk of overheating or engine failure, which could lead to catastrophic failure. These safety issues must be addressed before plasma engines can be adapted for commercial air travel. Despite these challenges, there are signs of progress in the development of plasma engines for air travel. In addition to the Chinese research team, many other companies and researchers are exploring the potential of plasma engines, including NASA and the European Space Agency. These efforts are focused on developing new technologies that can improve the efficiency and scalability of plasma engines and address safety concerns. As we move towards a future that emphasizes renewable energy and resource conservation, the development of plasma engines marks a crucial turning point in transportation. And with this revolutionary innovation on the horizon, we need to reflect, what other extraordinary advances could we achieve by exploring the full potential of plasma engines? How could this reshape the future of transportation as we know it?